All right, so tonight we're going to start chapter 3, the derivatives. So I think I've mentioned this many times. This is maybe the most important topic in the entire course. The derivative is an incredibly important idea, and we'll see it throughout the entire course, really. A lot of applications are defined in terms of derivatives, and what they're really all about is helping us understand how a function changes with respect to another variable. So we can see there'll be different ways of defining it. And what's also interesting is that if you look at the history of math, you'll realize that a lot of what we're doing here was jointly invented by two famous mathematicians, Gottfried Leibniz from Germany, and also, of course, Isaac Newton, who everybody knows. And so during the latter 17th century, early 18th century, they both worked on calculus independently of each other. And Newton apparently was very, very secretive about his results. He was very reluctant to publish anything until he was 100% positive that it was accurate. So a lot of what he did didn't see the light of day until many years after he developed it. And he was apparently not familiar with the works of Leibniz in Germany because I guess Newton was a genius, but I guess he didn't speak German. So he didn't read any of the papers written by Leibniz. And so they had no idea the other one was working on calculus. And so a lot of the same results were developed by both of them. But in a lot of ways, what ended up happening was that the notation that we use today is pretty much all taken from the works of Leibniz. But historians and mathematicians have given them both credit for jointly inventing the field. Of course, Newton was trying to laws of planetary motion, and he was also big time into fields like optics. And so he found that calculus was necessary to help explain what was going on in those fields. And so his motivation was because the math didn't exist at the time. He just said, we don't have this math that we need. Why don't I just invent it myself? He was at that level where he could create an entire new field all on his own. And so the reason why I'm bringing all this up now is because in this very chapter, we'll see at one point a couple of alternative ways of expressing the same results. And we'll end up using Leibniz's notation just because I think it's more straightforward and easier to follow. But, you could do it either way. And the book does mention them both. So anyway, calculus has been around for quite a few centuries now. The thing is, math actually has a very interesting history. Maybe one day, if we have a few extra minutes, we'll watch a couple of videos about the history of math and how it developed over time. You might be surprised to discover, for example, that the concept of zero wasn't even thought of until about the 8th or the 9th century AD. And a lot of the concepts that we take for granted now have only been developed relatively recently. In particular, this field here, which we know is continuous math, it's a relatively new thing compared to a lot of the other math that we use, which dates back all the way to well before Christ was born. So anyway, so here what we're going to do is define derivatives. You need to understand what they are in the first place, and then we'll see that there's different ways of calculating them. We can use the formal definitions, and then we can also use a series of rules, which once we understand the rules, calculating derivatives is not that big of a deal as long as the functions aren't horribly complicated. And of course, we can always use our friend Symbolab to lean on, or we can lean on our friend Symbolab to double check our results. And in some cases, it will actually show us how it got its results. So if there's any steps that we missed, we can see what happened. So anyway, this will be a big chapter, a very big one. Now, in the meantime, I just want to remind you that you're supposed to have your first problem set ready by midnight tonight. And so for next week, I've put a new one on Moodle, which is, let me go open it for you. Here it is. Problem set number 2, this is all limits. And of course, just like the last one, I've just chosen them all from the book. And so you can just go through and you can do them all and send them in next Thursday. Same thing, next Thursday by midnight. And all you have to do is scan your results either with a physical scanner. Maybe you can buy a software product that will make your phone into a scanner, And or you can just literally take pictures of your results with your phone camera and then just email them back to me. I don't know if it's possible to set up Moodle for you to deposit your documents there. I mean, it's possible, but as long as email works, we might as well just use it. And I'll let you know when I receive your work. And, I'll go through them all. And if I see that I don't have somebody's work, I'll write to you and let you know, because there's always a chance that it disappeared into my junk box. That's one of the drawbacks about email. It's not 100% reliable, as you know. And I discovered this the hard way while the COVID was going on. You'd be surprised how many times people sent me documents that never arrived, not even in my junk box. What can happen is when the documents start getting very large, which they will when you start taking pictures, strange things can happen to those emails. So I will let you know if there's a problem. But for the most part, you can just go ahead and send me everything back by email. That should do the job, especially with a relatively small class. So anyway, let's take a look at our exciting topic here, derivatives. So we're going to be looking at the derivative itself, the rules of differentiation, and higher order applications of it. And so we're going to start by revisiting this concept of secant lines, because as we'll see, the derivative is ultimately determined in terms of secant lines as they converge to tangent lines. Okay, so if we have a secant, let's remind ourselves what that looks like. You have a straight line that cuts through a function at two different points. And you can see in the bottom there, the slope of that secant line is, so if we take this as point number 2, let's say, and this could be thought of as point 1. The slope for any line, as you know, can be written as delta y over delta x, which in turn can be written as y2 minus y1 over x2 minus x1. Okay, and so here, though, you would think of this as x2, this is y2, x1, y1. And so that's what this represents. It's y2 minus y1 divided by x2 minus x1. So in that sense, it's no different than any other straight line slope you've ever calculated before. It's just that the notation looks a little bit different. So that's the slope of our secant. Now, we're not really interested in the secant itself. What we're really after is the slope of the function at this point right here, which, as you can see, the secant line the slope of the secant line is not equal to the slope of a tangent line that you could define at this point. So this would be roughly what a tangent line would look like at that point. And you can see it's not the same as the slope of the secant line. But if we move closer and closer, in other words, if we try another point, let's say here, and we define another secant line through this new point with the original point, well, you can see the slope will be a little closer to the tangent line. So if you think of this as, I'll call it secant line 1. I'll call this secant line 2. As we keep moving the second point closer to the first point, the slope of the corresponding secant line will get closer and closer to the actual tangent line that we need. And so you can see this opens the door for us to use limits. Okay, in other words, what we're trying to do is define the limit as these 2 points keep getting closer and closer to each other. And in the limit, the secant line will perfectly coincide with the tangent line, because the difference between x2 and x1 would actually be 0. So what we're going to essentially do is apply the limit to the slope. to come up with the proper formula for the slope of this tangent line. Once we have that, then we can calculate our derivative. All right, anyway, so let's take a look. Now, as I said before, there's actually different ways of going about what we're doing here. That approach that you're seeing there is very useful, but for the most part, we'll be using this approach instead. And you can see it's a little different. We've introduced this new variable h, and h is meant to represent, well, let me show you the graph so you can see what's going on with that. Instead of using x and instead of x and f of x, we're going to think of it a little differently. H is meant to represent the difference between these two x coordinates. Okay, in other words, the change in x is equal to a plus h minus a, or just plain old h. And so if we take the limit as, well, the limit of the slope of the secant, as this difference gets closer to 0, will give us the slope of the tangent line at that point, of course, a f of a, which in turn will turn out to be, this is what we mean by the derivative of f of x at the point a comma f of a. So in other words, we can use the geometry to visualize what's going on here, but as far as the actual calculations are concerned, we're actually just taking a limit of the slope of this tangent line as the difference between the 2 points shrinks up to 0. So then all we have to do is apply our limit rules, and we'll come up with the result that we're looking for. Okay, now what's going on here is it's basically showing you what I just told you. You're getting, they're showing you what happens when you keep getting closer and closer to the original point, but they're also showing you how the two definitions are slightly different from each other. This is the first one we did, and this is the second one, and they amount to the same thing. It's just that I personally find that this one is easier to follow. It's just easier to keep track of what's happening, even though they both represent the same thing. And of course, in both cases, once the limiting case is this tangent line, which is what we're looking for. Okay, now, so we're going to do an example of this right now. So let's just say that we want to solve for the slope of the tangent line to this function. Now, the function is assumed to be x squared, and the point that we're interested in is x equals 3. So let's say right here, this would be the point 3 comma 9. And so what we're aiming for, trying to draw the line as close as I can get to it. Just barely touching. Ooh, not bad. Okay, so what we're really interested in here is the slope of this tangent line. Now, why does that matter so much? What's the big deal? Because the slope represents, as you may recall from chapter 1, the rate of change of this function at that point. So in other words, it's going to tell me what would happen to y if x changes ever so slightly. So if I increase x from 3 to, let's say, 3.1, I want to know what happens to y. That's what this is going to give me. Now, you can imagine applications for that. Like, for example, if this represents the point at which I'm producing a product, and I want to know what the impact is on my profits of changing the amount of output I'm producing, this is exactly what I would do. Okay, I would come up with a function for my profits, And I would come up with a slope, and I would understand right away, if I increase my output by, let's say, 1 unit, what will be the impact to my profits? Okay, so that's why we're so excited about this slope, because it represents the rate of change, and that knowledge will be helpful for some reason. So anyway, we're going to approach this in 2 different ways. And again, remember, there's 2 different ways we can do this. So this time, unlike before, we're looking at the slopes of our secant lines. Now this formula is designed to tell us the slope of our tangent line. So we're going to apply this definition to this function where x equals 3 and see what we come up with. Okay, so keep in mind, the little a there is 3. The function f of x is x squared. Okay, so actually I'll just put that up here to remind ourselves. So this function, actually, let me copy this here, just so we don't have to go back and forth a million times. Okay, that's what we're trying to do right there. Okay, great. So first thing I did was I replaced all the a's with 3's, okay, including here. And then the f of x's are replaced with the x squared, of course, because that's the name of the function. So the important thing here is that f of x is x squared, but f of a is therefore 3 squared. The function is x squared. Since a is 3, what I'm basically doing here is evaluating this function where x equals 3. Okay, in the denominator, we just leave these the way they are. Now, we're going to run into a problem. We've seen this before in chapter 2. If you look very carefully at this result, you'll see that if I plug 3 directly into this function, I'm just going to wind up with 0 over 0. Okay, but we already know what to do about that. What we're going to do is we're going to simplify it. So to nobody's surprise, substituting 3 for this, for these x's, the final step would be to replace all the x's with 3's, and we end up with 0 over 0. So what can we do about that? Well, what we're going to do is factor the numerator of this expression to x minus 3 times x plus 3, so that these 2 drop out. And we end up taking the limit of x plus 3 as x approaches 3, and we end up with 6. So that means that the slope of this tangent line at the point 3, I'll just pencil it in here, does in fact equal 6. So that means that now, if x increases by some small amount, let's say we'll call it h, then y increases by 6h. Okay, that's what it tells me. And of course, it also means that if x decreases by h, then y decreases by 6h. Okay, so it's a very steep tangent line. And that tells me, so now I know, if I change x by a certain amount, what is the impact on y? Now, just want to point out here, though, that this is only accurate if h is very small. So in other words, if I try to change x from 3 to 20 or some nonsense like that, the result will not be very accurate. This technically is only true in the immediate neighborhood of 3. So the accuracy of what we're doing here is only going to be very high if the change in x is very, very small. Okay. All right, now we're going to do the same thing. Oh, and by the way, this is what it looks like. The book has kindly given us a graph so you can see exactly what happened. You can see the slope of both of them is 6. This is the tangent line at that point. Here's the 9. And so at that point, the slope of the tangent line is 6, which means the rate of change is 6. And it also means the derivative of the function, which we'll define more formally in a few minutes, is 6. All right. So now we're going to take the other approach. Now, remember, I did mention that there's 2 different ways of doing this. We have this approach, and then an equivalent version of that looks like this, where, again, the h represents the difference between the 2 points on the function. So in other words, the h is simply the difference between the 2 x coordinates. And you can see that what we're going to do is we're going to take the limit as that distance between them gets smaller and smaller, and in fact converges to 0, so that in the limit, the 2 points coincide with each other. So of course we expect to find the same result, and we will, but we're going to go about it slightly differently. And by the way, this is the approach that we'll use most of the time. I personally find this to be more useful, but and the book apparently does too, because most of the examples are done this way. So yeah, let me just copy this here so you can see it again. Anyway, so again, once again, the function is x squared, and x is 3. At x equals 3, and that means that a is, actually what I should say is that a is 3. Because if you look at that diagram, that a represents the x coordinate for the initial point, so we can just write a equals 3 here. You notice that x is not even in this formula. Instead, we're calling it a and a plus h. So, we plug in 3 for all the a's. Now we apply the function to both 3 plus h and 3. So in other words, in this first case, we'll have 3 plus h squared because the function is x squared. And here we'll have 3 squared, again, because the function is x squared. And then the rest is just algebra. So if you actually square this out, 3 plus x, h rather squared, if you use FOIL, you'll see that that's equal to 9 plus 6h plus h squared. Then you subtract 9 from that, and at the end you divide by h. Now, of course, what we're going to try to do is keep simplifying this as much as we can before we actually try to take the limit. We try to plug in the 0 now, we're going to run into the same problem as we had before, which is 0 over 0. So rather than doing that, we're going to simplify this until it's no longer possible, and only then will we try to take the actual limit. All right, so, oh boy, that worked out nicely. So first of all, these drop out. And then if you notice, you're left with, it's on the next slide, 6h plus h squared over h. And of course, both of these terms in the numerator have h as a common factor. So this reduces very nicely to 6 plus h. And so now direct substitution gives us the result we're expecting, which means 6. Okay, so that wasn't too painful, was it? No, it was not. But either approach is fine. Now, we're about to finally, for the love of God, introduce the formal definition of a derivative at a single point. And you'll see that it has 2 equivalent ways that we can express it. All right, and what could be those ways? Well, I think you will not be surprised to see this. I just want to point out as a point of notation, for a function f of x, f prime of x equals the derivative of x. And there's different ways of writing this, by the way. This can also be written as dy dx. The d, basically, here's what's going on with that d. You're all familiar with the idea that delta y over delta x is the slope of a line. So when we're looking at a tangent line, remember the derivative is defined in terms of the slope of the tangent line. What separates this and this is that the delta is a small change. The d represents an infinitesimally small change. So essentially, you can think of this as the result of shrinking up the delta as it approaches zero. It converges to this d, or the d is known as a differential. It's essentially the limiting case of delta y and delta over delta x as delta x approaches zero. So when we're talking about derivatives, this is the one we normally use. Okay, and then sometimes you see this also written as y prime. Okay, there might be others, but if there are, they're very rarely used. Those are the most important ways of expressing the derivative. We tend to use the one that makes the most sense for that particular type of problem. Like, for example, there's a technique called implicit differentiation we'll learn later on, where we tend to use the y prime. It's just easier. For other types of applications where we're using polynomials, there's a tendency to use the f prime notation. Dy dx is useful for other types of situations. So, we tend to pick and choose the one that we use. But the most common, I would say, is the f prime of x notation. But they all mean the same thing, so just keep that in mind. And in fact, we're actually later on today, we're actually going to use the dy dx notation at least once or twice. So anyway, you can see those are the two equivalent versions of the definition of the derivative at point A. And they're both limits. In fact, they're exactly like what we were just doing. In the first case, we're defining the 2 points on our curve function. The first point is always a comma f of a. The issue here is, what are we calling the second one? So in this first case, we're calling this x f of x. In the second case, the 2 points are a f of a, and this one is referred to as a plus h comma f of a plus h, just to reinforce the notion that h is nothing but the difference between these 2 points, the 2x coordinates. So what we're going to do, and by the way, one more thing. I've got here f prime of x is the derivative. F prime of a is the derivative evaluated where x equals a. In other words, we're calculating the derivative at a specific point in the curve. The f prime of x will give us a formula that we can apply to any point in the curve, but f prime of a means what happens at point A. Okay, so that's the difference between the two. All right, so let's do one. Now, by the way, this is we're essentially just taking what we did earlier with the limits and applying them to find a derivative. It's the same example. The function is f of x equals x squared at the point x equals 3. So we'll start with the first definition. Same thing, y equals x squared. Here's the point 3 comma 9. Now, of course, we already know the answer. The slope of the tangent line we've already determined is 6. Okay, but let's look at another way of finding out. And of course, this slope is the derivative. F prime of 3 is 6. That's what we're saying here. The derivative when x equals 3 is 6. Now let's see why. Okay. So we're going to plug in all the numbers, and then we're going to take the limit. And of course, just like before, we're going to run into the problem of 0 over 0 if we only just directly substitute. But we know how to work around that. Okay, so this is f of x. This is f of 3. And this is just x and a. And when you plug in the 3 here, you're going to wind up with oh no, 0 over 0. Our nemesis 0 over 0 has returned. So, but we already know that that's not a problem because we can factor out the numerator and there will be enough simplification so that we can solve for this directly. Yeah, there it is. So remember, this was x squared minus 9. And you can double check this with FOIL if you want to. And you'll see that these drop out. You end up with limit x plus 3 as x approaches 3, and we get a result of 6. Now, by the way, this calculating derivatives with this limit definition is something we're only going to do once right now when we're introducing this topic. After this, we're going to just use the rules. But it's important to understand what the rules, the definition is telling us. But once we've gotten past this point, from now on, after that, we'll just use rules. So, it's kind of like learning how to drive with a stick shift. Why would you ever want to do that? It's just you need to know, but after that, you can use automatic for the rest of your life. Okay, so for this approach, once again, remember that a is 3, f of x is x squared. So we'll plug in the numbers and go through all the same steps we had before. And here at the end, you can see that we have a lot of cancellation. These drop out. This one reduces to the limit as h goes to 0 of 6 plus h, which is just 6 because h goes to 0. All right, so I think we're getting pretty good at this. Oh, we've got one more. All right. Okay, we probably could use enough. Let's just say we could use the practice for one more. Let's try a different one for a change. Let's do this one. Let's say that the function is x squared plus 3, and we're interested in knowing what is the derivative when x equals 2. So that would be the slope. That's f prime of x when x equals 2. So we call it f prime of 2. So we're going to use, remember I said before, there's these two different approaches. We'll use this approach. I don't know if there's an actual proper name for this, but we're using this approach most of the time. And so we'll start with that. And just a quick reminder, f of x is x squared plus 3. So that means here, you need to not only square what's in the parentheses, but add 3 at the end. Okay, don't forget about that. The function is x squared plus 3. So you're squaring a plus h, and then you're adding 3 at the end. And similarly here, you're squaring the a plus you're adding 3. Okay, so that's going to make the algebra a little bit messier, but not that much. And then, of course, at the end, we divide by h, and we take the limit as h goes to 0. Very good. So, and of course, we also need to evaluate this when x equals 2. So once that's done, we're going to plug in. Well, actually, we're not going to plug in anything just yet, except, oh, wait a minute. No, yes, we are. We're going to replace the a's with 2's. That will be the next step. Okay, that'll make things a little bit simpler. So this is what it looked like. Well, actually, no. What I've done in this next step is replace the a's with 2's. And then you can write out the steps. Now, all of this is 2 plus h squared. Then we have the 3. And then now here we have to drop the parentheses. So we have 2 negatives here. This is 4 and this is 3. So you can see that all that simplifies down to 4h plus h squared all over h, which of course is the same thing as the limit of 4 plus h. Oh yeah, it's 4. And that's the slope of the tangent line at that point, which means that is the derivative of the function when x equals 2. Or think of it as the rate of change of the function when x equals 2, because it means the same thing. Okay, so in the book, from now on, this will be the approach that we take. We're going to write it like this. The derivative will now, from now on, be formally known as this. This is, if somebody says to you, what is the formal definition of a definition, a derivative, this is what you're going to do. Okay. And you can see we've chosen the version where h is in the denominator. H is, again, the difference between the 2 points on the function. We want to know what happens as they get closer to each other. So we're going to apply this to a couple of examples before we introduce the rules. Before we do that, we just want to mention that not every, up to this point, we've been assuming that the function we're working with actually has a derivative. It turns out that some functions, either they do not have a derivative at all, or else they do not have a derivative over certain ranges of the function. So just as in a nutshell, well, first of all, there's a formal definition. A function is said to be differentiable if at a point A, if the derivative exists at that point. And that requires that, number one, the function has to be continuous at that point. And number two, it must have a unique tangent line at that point. So you're probably wondering, well, what would cause the function not to be differentiable? All right, let me show you a couple of examples where this is a problem. How about this one? Let's say at the point x equals 3, oh no, we have a hole in our function. So clearly the function is not continuous at x equals 3. So everywhere else is fine. So f of x is not differentiable at x equals 3. And I'll put in parentheses here, but is differentiable everywhere else. So in other words, if we needed the derivative where x equals 3, we'd be out of luck because it does not exist. And so we can run into this for very strange functions. Tend not to run into this. There's certain disciplines where you tend not to have discontinuous functions, like in economics. If this is your profit function, you're not typically going to have a sudden jump in the function. It doesn't usually work that way, but in other areas of study, you might run into this. So it just means that there just is no derivative there. It's undefined. Another case, a very bizarre case that you can run into, is this one, where the function is actually continuous, but there's a real problem here. Now, I haven't drawn it maybe as well as I could have, but the point of it here is that this region of the function is flat. And so that means that there isn't a unique tangent line there. There's different tangent lines you could draw through there. Oh, like this one. And this one. So in other words, it's not considered to be differential. Let's say this is the range between A and B. Yeah, that's what they meant by having a unique tangent line. Now, there's actually a third case, which we'll run into again later on, but right now, it doesn't say it here, but I just want to show it to you before we go any further. Um, just keep in mind the whole purpose of the derivative. Um, the derivative had, let's put it, let's see how can I explain this? Okay, let's try this. If a function has a derivative at point A, it means that the function slope is converging to the, actually, let me make it more clear than that. The slope of a tangent line is converging to f prime of A coming from the left and the right. So it's just like with limits, we have limits coming from the left and limits coming from the right. You can actually calculate a derivative coming from both directions. So let me show you a graph where this should be clear. So let's say this is some point A. This is f of A. So what I'm trying to get at here is that if I were to draw a bunch of tangent lines from, let's say, here, and then as I keep getting closer and closer to A, the slopes of these tangent lines is getting very close to the actual derivative. And if I do the same thing from larger values, let's say I start by defining a tangent here, and then here, and then here. On either side, the slopes of those tangents are getting closer and closer to this point. Okay, so that's good because that means the derivative is defined at that point. The tangents are converging to f prime of A coming from the left and the right. They're both heading in the same direction. You know, it's kind of like two people are trying to meet up at that point A, and even though they're coming from different directions, they're gradually getting closer and closer to their destination, and so eventually they'll meet at point A. It's not exactly the same thing, but here it's the slopes of the tangents that are getting closer and closer and closer. So that means that the derivative is in fact defined at that point. So let me show you a case where that would not be true. Suppose that the function is our old friend, absolute value x. Now, there's a problem here. F prime of 0 is undefined. Why? because the slopes on this side, any tangents that I choose to draw, the slope is 1. On this side, any tangent I choose to draw is -1. They're not only are they not the same, they're not even getting closer to each other. The slope on the left-hand side stays at -1. The slope on the right-hand side stays at 1. They do not ever converge to each other. And so at that point right there, the function has no derivative. So, and that's again because the tangents are not converting to each other or converging to each other on the left and the right. So anytime you have a function with a sharp break like that, it doesn't have to be this one. Let's say you got something like this. Right about here, the derivative is undefined. This is point A. And it's the same logic. So you should be able to tell from the graph when this is happening. We'll call it informally a sharp break, but what it really means is that the limits are, the slopes are different on either side of that point. And that's bad news. That means no derivative at that point. So anyway, now what we're going to do, we're going to get some practice calculating derivatives using the formal definition. So let's start out with something simple. F of x is the square root of x. Okay, so what's the derivative? Now, we can, by the way, and whenever we're doing a derivative, there's going to be two things we can do. We can have a general formula, which tells us the derivative at any point in that curve. And then we can find the derivative at a specific point. Okay, so in other words, if right now what we're trying to do is come up with a formula that represents the derivative at any point that we choose in the curve. If we need a specific point, then we can plug it in to the derivative that we calculate. So once again, here's the formal definition. And this is a specific case because f of x is radical x. We're replacing this with radical x plus h, and this is replaced with radical x. Now, it appears that we have a mess on our hands, doesn't it? But we already have seen an example just like this the other day. That involves something called a conjugate. So let's remind ourselves the conjugate of a plus b is a minus b. And the product of these two is guaranteed to be simply a squared minus b squared. So does that give us ideas? Yes, it does. What we're going to do to simplify this and so it might not seem like it, but that's going to make it possible to consolidate all these terms, because if we don't, guess what we're going to get? Without this simplification, direct substitution, as is so often the case, will end up giving us 0 over 0. Okay, so instead we'll try this conjugate approach, and it's all written out right here. So if you think of this as A and this is B, that means that what we have here is radical, x plus h squared minus radical x squared, which just now when you square root, you're just basically canceling those operators out. And so you just end up with h. Okay, 8x plus h over minus x. In the denominator, you just have the product of these two. And again, that looks like we're getting into trouble. It's going to be a horrible mess. But in reality, there will be enough cancellation that we can directly solve for this limit with substitution. Well, all right, let's see how that works. So we're all relieved to hear that because it looks terrifying, but guess what? The h's cancel each other out. And now when you plug in the 0, it becomes so simple. 1 over radical x plus radical x, or 1 over 2 radical x. And let's remind ourselves that this is the same thing as x to the negative 1/2 power. So therefore, if we have 1 over 2 times radical x, it's equal to 1/2 x to the minus 1/2 power. And that's it. So again, if we needed to know the derivative at a specific point on the function, all we have to do is plug it in for x, and we have our answer. Very good. Now, sometimes, of course, the trick here is that you have to know how to simplify your result. But after you've done enough of these, you'll start to get a good feel for this. Sometimes we can use conjugates. Sometimes we can simply factor them in different ways and see what happens. All right, well, this next one looks like it's going to be more straightforward, but I wouldn't count on it. Okay, it's actually a little bit messier than it looks. But let's see what we can do. Let's find the derivative of this function using the formal limit definition. And so let's take care of that on the next slide. What I'm going to do is copy this function onto the next slide. Right about here, I guess there's some space. Not much, just enough. Oh, there we go. Okay, well, it's still a little awkward here. Just as a quick reference. Okay, so now here's why I say it's a little challenging, because what is f of x plus h? Well, the function is x squared, so that means we have to square x plus h, but then it's also minus 2x, so we have to say minus 2x plus h. Over here, it's easy, it's just the function. So we have to be very careful when we evaluate the function at x plus h. Basically, all you're doing is you're replacing all the x's with x plus h's, but you have to be careful. Okay, now this part, if you use FOIL, you'll confirm that this is true. Here I'm just multiplying. -2 by x, -2 by h. Over here, I'm simply dropping the parentheses, so I've got negative x squared, but plus 2x, all divided by h. Now, of course, we don't want to solve for this directly because we'll end up with 0 over 0. But luckily, a lot of these terms do cancel each other out. So if you gather up all the like terms together, you'll see that several of them do drop out, which is always helpful. So what do I mean by, let's see how that turns out. For example, these two cancel each other out. What else? Here we go. These two drop out. Well, that's very helpful. Looks like the rest of them stay, and so we end up with this. But guess what? Each one of them has a common factor of h, so we can just cancel that out. We end up with 2x plus h minus 2. And when you plug in 0 for the h, here's your answer. Well, what do you know? So when you first look at these notes, you look at it and say, oh my God, this looks like a nightmare. It really isn't. It just takes a little getting used to. And like I said, this is going to take a lot of time compared to simply applying the rules that we're going to learn. But it's awfully important to understand what the derivative actually means. Okay, now, by the way, just for completeness sake, there's a theorem that tells us that if a function is continuous, sorry, if a function is differentiable, let's say here, that guarantees that the function must be continuous at that point. Okay, so in other words, you don't have to worry about continuity. If the function, if we can find a derivative at that point, that guarantees that the function is continuous. All right, now here's an interesting concept. The derivative can be applied to a function more than once. Oh, that's interesting. You can apply the same rules basically as many times as you like. And when you do, what you're actually doing is taking what are called the second and the third derivatives. The function that we just, or the techniques we just learned, is f prime of x, is formally known as the first derivative, although usually just say the word derivative. But technically, this is the first derivative because we've only applied our rules once. If you want to try this a second time, you're calculating what's called the second derivative, and we'll express that as f double prime of x. And then the third derivative, as you can imagine, is f triple prime of x. Now, in practice, I guess it depends on the discipline. In economics and finance, you almost never need a third derivative. It's very, very unusual. Most actual applications at most require the first and the second derivative. But in principle, there's nothing to stop you from going up and taking the fourth and the fifth and the sixth derivatives. Although eventually, if you do this often enough, eventually you'll end up at zero. So there is a limit to how far you can push this. But you just need to be aware that there do exist what we call higher order derivatives. And we'll see them as we go along, especially, like I said, the first and second derivatives. You might need the third one in physics, but economics and finance, it's not going to happen. Okay. And by the way, just when you think about it, the second derivative is just the rate of change of the first derivative. It tells me how quickly the first derivative changes. That's really what it is. And then the third derivative is the rate of change of the second derivative. Okay, now, by the way, as you can probably imagine, notation-wise, since there's more than one way of expressing the first derivative, there must also be different ways of expressing the second derivative and the third. What might they look like? Well, let's check this out. To remember the first derivative, the three options we had were f prime of x, y prime, dy dx. The second derivative is very logical based on the first derivative. F double prime of x, y double prime, d squared y dx squared. The two reminds us that this is the second derivative. In fact, formally, this is this. In other words, this reminds us that you're just simply reapplying the derivative. All right, well, of course, what you can probably guess what's coming next, the third derivative. In fact, just jump ahead right now. And there's no big surprises coming here. F triple prime of x, y triple prime, d triple y, d cubed y dx cubed. This is you're just applying the derivative again to the second derivative, or if you really want to get carried away, That's it. That's what you're doing. Well, now it's time at long last to introduce the rules. Okay. I think once you'll see the rules themselves, once you get used to them, you'll see that it's much easier to calculate derivatives with the rules than constantly trying to use the limits. The limits do take a while to use and they can get horribly messy. The rules are pretty straightforward, although they're messier than the rules that we use for limits. In particular, when we have quotients, the rules can get really messy. But let's just see, how many are there? We've got 7 of them that we'll go through. Although one of them we're going to save it for last because it is kind of complicated. The first 2 couldn't be any simpler. The so-called constant rule, where we're trying to see what happens when we take the derivative of a constant. The power rule just refers to a simple cases where we have x raised to some constant power. Those are, the 2 basic rules. And then what we're going to do is see what happens when we're applying derivatives to functions, more than one function at a time. In other words, for example, sums and differences, products and quotients, a more advanced version of the power rule, and then finally the so-called chain rule, which in this book, at least, they kept it in a separate section. So that will come later, only because it's fairly involved. All right, let's start with the simplest one. The constant rule should come as no surprise to you. The derivative, remember, is a rate of change. If we have a constant k, it never changes. So by definition, the derivative of a constant is simply 0. Okay, that's all there is to it. As soon as you see a constant, its derivative is 0 because it doesn't change. Okay, it doesn't matter what the constant is, its derivative is 0. And if you want to think about it, like for example, this. Hold on one second. Let's say, a constant can be expressed as a horizontal line. If y is equal to 7 or f of x is 7 and it never changes, this is what the graph looks like. And you can see the slope of this thing, which is delta y over delta x. The problem here is that delta y is always 0. So the slope is 0. Now remember, the derivative is a slope. So it stands to reason that the derivative of this function is always going to be 0. And again, the logic is that this is a constant, it can't change, so therefore the derivative must be 0. Very good, that's easy. We like that one, it's very easy. The power rule is a little bit more challenging, but once you get used to it, you'll see it's not that complicated. So because it's a little bit more complicated, I'll tell you what, let's save that one for after the break, and we'll pick it up from there, and we'll dive into these more complicated rules, and we'll do several examples just to make sure we really understand them, okay? It's the kind of thing where once you get a little practice, you'll find that they're not difficult at all, but we do have to get used to them. Okay, so we'll stop here. We'll come back in a bit, and then we'll have our break. And then when we get back, we'll introduce ourselves to the rules of derivatives. Okay, so I'll give you time to recuperate from all that, and then we'll carry on. All right, so ready for really one of the more important rules. We'll see this all the time, the so-called power rule, where what happens is, imagine you've got a number, x raised to some power times a constant. The formal rule is this. Let me just copy this. And it looks scary again, but once we've done a few, you'll say, oh, well, this is not that hard. And that's because it's not. Let me just make that a little bigger. So, oh my God, what happened there? The derivative is then n times k times x to the n minus 1 power. Now we're assuming that k and n are constants. Okay, they're real numbers. So let me just show you a quick example of this. Suppose that we had f of x is 5x to the 4th power. So that means that this is k and this is n. So according to the rule, f prime of x is equal to 4 times 5 times x, and then the exponent is 4 minus 1. Or we can simplify this to 20x to the 3rd power. Okay, so like I said, it's not conceptually very difficult. And once you've done a few of these, it'll start to become second nature, but it really is one of the more important rules. So we want to make sure we understand it. Whatever the exponent was, you're multiplying the entire result by that. And then you're adjusting the exponent by subtracting 1. The constant, or the coefficient, I should say, is not going to change. The 5 is staying in front of the x. It's really just the exponent that we're using to come up with this result. So, all right, what the heck? Let's do another one. Let me show you another one. Suppose we have three x to the 6th. Now remember, this is taking the form k x to the n, and that tells me that k is 3 and n is 6. So the rule says to do this: n k x to the n minus 1. So that tells me that my derivative is 6, the exponent times the coefficient of 3, and the exponent is reduced by 1 to give me 18x to the 5th power. Okay. Actually, hold on a sec. I have to go close this window. It's getting very cold in here. I'll be right back. All right. So anyway, this is how we treat these cases. Let's do a different one, a little slightly more challenging one. Let's say that f of x is 2x to the minus 3 power. Now, just because this exponent is negative doesn't really change anything. This is k, and this is n. So remember, what we need is the exponent comes down in the front. The coefficient k stays the same. But now we're subtracting 1 from this exponent. It's actually now minus 3 minus 1. And so you're going to wind up with minus 6x to the minus 4 power. So the negatives can make it a little bit more confusing, but the rule really hasn't changed. Nothing is different. You're taking the exponent, multiplying that by the entire expression, and then you're adjusting the exponent. Okay. All right, well, while we're at it, let's do another one. Let's have two negatives. Let's say f of x is minus 2x to the minus 4 power. Okay, this is k. This is n. The derivative is nkx to the n minus 1, which means minus 4 minus 2x to the minus 4 minus 1, 8x to the minus 5 power. Interesting. All right. Now, here's another one that you'll find interesting. What if I have something like this? Just plain old 3x. Now, remember, when you see something like this, there's an implied exponent of 1. So the k in this case is the 3. The n is the 1. So when you go to take the derivative, what you're going to have is 1 times 3 times x. And now look at this. The exponent is 1 minus 1, which is, of course, just 0. So you end up with just plain old 3. Okay, because again, the x has an exponent of 1. When you subtract 1 from that, it becomes 0. And anything raised to the 0 power, of course, is just 1. Sorry, yes, anything, right, exactly. So in other words, what this is technically 3 times 1, but we just write it as 3. Okay. Now, I'd like to show you another interesting case. What if I have this? Oh, wait a minute, it's a constant. And we already know that the derivative is simply 0. But what if we write it like this? Oh, yes, we can do that because x to the 0 power is just 1. So this becomes our k. And this is our n. So in this case, I'll end up with 0 times 5x to the 0 minus 1 power. The exponent doesn't matter. We're just going to wind up with 0. So in other words, what we just got through proving or demonstrating is that the power rule, or sorry, the constant rule is a special case of the power rule when n equals 0. Well, so this one, either you can apply either one. You can just use the constant rule, which is nice and quick. But just remember, this is really just a special case of the power rule. Now, sometimes you're going to run into some very messy examples of this. Let's try one like that. What's going on with this one? Well, remember, this is the same thing as 3x to the 1/2 power. So given that the derivative is nkx to the n minus 1, we're going to have 1/2, 3, x to the 1/2 minus 1. 3/2 x to the negative 1/2 power, which is the same thing as this. Or you could just rewrite it as 3/2 radical x. Because remember, a negative exponent means you're actually taking the inverse. And of course, the square root is just x to the 1/2 power. So that one's a little bit messier. But you can have these. You can have fractional exponents and you can have negative exponents. And sometimes you can have both. And it gets really messy. So let's come up with an example of that. Ooh, a negative exponent. All right. So we're going to have negative 1/2 times 4 times x to the minus 1/2 minus 1. So you're going to wind up ultimately with negative 2 x to the minus 3/2. And if you chose to do so, you could rewrite this like this. It's not necessary, but just be aware that they mean the same thing. So that's our power rule. And it's really, like I said, even though sometimes, you might have messy results, it's really not that difficult. And we'll see that probably more than any other rule. All right, I see that there's still a few more examples left in the slides, like this one. Here's our K. Here's our N. And so what do we do with this one? And again, this is our K and this is our N. So we're going to end up with 4, 3, x to the 4 minus 1, or this reduces very nicely to 12x cubed. Oh, that wasn't too bad. All right, I think there's one more here. Let's just look at it. I think by now we're getting pretty good at this. So let's try one with a negative exponent again. In fact, I'll tell you what, why don't you write it down on a piece of paper, and before I show you the answer, this is K, this is N. Remember, the derivative is nkx to the n minus 1. So just take a second and figure it out. All right, so let's jump ahead to the next slide. We'll see how this is done. So you've got, remember, the original function was 6x to the minus 3. So you now have negative 3 times 6, x is minus 3 minus 1, and the final result is negative 18, x to the minus 4. All right, so those are really the two basic cases. Now we can look at the cases where we're actually combining multiple functions. For example, what about if we're adding two functions together or subtracting? How do we calculate the derivative of a sum or a difference? Well, this one is very easy. Okay, let me show you. What if the function f of x consists of two other functions that we add together, g of x and h of x? Well, then the derivative of x, f of x, f prime of x, is equal to the sum of the derivatives of g of x and h of x, and it's that simple. Wow. And of course, for some differences, you just subtract instead of add. Okay, so that's all you have to do. Well, that one's nice. Now, unfortunately, the products and quotients are kind of messy, but this one is very simple. So let me just quickly show you how the differences look. So you just change the sums to differences. That's all you have to do differently. Okay, now let's take a look at this example. Now, if you notice, if we treat this as g of x, and this is h of x, you notice each one of these can be solved individually with a power rule. So let's just say g of x, 3x squared, g prime of x. The rule hasn't changed. It's nk x to the n minus 1, 2, 3 x to the 2 minus 1, which is just 6x. H prime of x, actually h of x, x cubed. Now here, by the way, there's an implied coefficient of 1. So don't forget about that. So that means that k is 1 and n is 3. So you'll have 3, 1, x to the 3 minus 1, which is 3x squared. And now all you have to do to come up with the derivative is add them up. You've got two separate derivatives. We just add them together. And so we end up with just 6x plus 3x squared. Well, that was nice and easy. If only they could all be this easy. All right, so now this is where it gets a little bit more complicated, the product rule. Now, again, it looks like a nightmare, but it really isn't. You just need a little practice with it. And so here's what happens. If I have two functions, f of x is a function of two other functions, g of x and h of x. So if f of x is the product of these two functions, this is what the derivative of f of x looks like. So you've got the first function times the derivative of the second function plus the second function times the derivative of the first function. And that's how it's done. So the challenging part, if you're doing this class in person, you would have to memorize this. And if you're taking Calc 2, you'll still need to memorize it, by the way, because most likely you'll be doing this in the classroom. But this is something that you most likely would be asked to commit to memory because it's so useful. Well, okay, so let's start with a basic case. Now, by the way, sometimes this proves not to be necessary. In the next example that I have here, it's so simple that you really don't have to use the product rule. You'll see what I mean in a second. Okay, actually, I'm going to copy this. Oh, that's not what I wanted to do. There we go. Just to have it as a reference point here. Okay, so you can see now what I was talking about. In a case like this, rather than using the product rule, what you could do is just multiply it out, and you'd have 6x to the fifth, and then f prime of x, because this is our k and this is our n. You would have 5, 6, x to the 5 minus 1, 30x to the 4th, and you'd be done. But let's just say that you decide that you need the practice. So you've got your g of x, your h of x. What you should probably do first is calculate g prime of x. And again, this is just our old friend, the product rule, or the power rule. You're going to have 2 times 3 times x to the 2 minus 1 power. So your g prime of x is 6x. H prime of x will be 3 times 2 times x to the 3 minus 1, or 6x squared. And now we can just use the rule right here. You can plug in, we have all 4 terms. We have g of x, we have h of x, we have g prime of x, and we have h prime of x. We'll plug them in and then we'll multiply them out and see what we get. And you'll see it's exactly the same. So we'll do that here. So let me just quickly remind you. G of x was 3x squared. H of x was 2x cubed. G prime of x is 6x. H prime of x is 6x squared. And so plugging these in, you can see down here we've done exactly that. Then you'll end up with 18x to the 4th plus 12x to the 4th. And just as we predicted, we end up with 30x to the 4th. All right, I think we can use a little more practice. Let's come up with one that's just a little bit messier. Okay. So how about this? Okay, so of course I will need g prime of x. Now, as far as that's concerned, what I can do here with a simple polynomial is I can apply whatever rule I need to each of these terms. So in other words, what I'm basically doing is calculating separately the derivative of 2x squared and 1 and adding them up. This one requires the product rule, the power rule, 2 times 2x to the 2 minus 1. This is a constant, so you can just write it as 0. So the final result there is simply 4x. Okay, so remember, that's where this is coming from. Okay, this is just a constant 0. Now for h of x, we're going to use the power rule. 7 for x to the 7 minus 1. Okay, because remember, this is your k, this is your n. So this is n k x to the n minus 1. So h prime of x is 28x to the 6th. So we know, in fact, let me go copy it. Oh, here it is. How this works. So now you just plug everything in. So 2x squared plus 1. Actually, I'm going to run out of space here. Let me move this. That's the actual answer. Now, you can simplify this if you want to. It isn't necessarily always true that you must do this. Like, if I was giving this test in person, I would certainly accept this as the answer. If there's some reason why you need to combine these, you can certainly feel free to do that. In fact, why don't we do that just to see what it looks like? But it's often not necessary. What do we have here? Now, when you multiply these together, you're basically multiplying both of these terms by this 28x to the 6th. So you've got 56x to the 8th, because you're adding these two together, plus 28x to the 6th. And when you multiply these together, you're going to end up with 16x to the 8th power, because you're combining this with 1. Remember, there's an implied 1 here. So this one could be simplified as 72x to the 8th plus 28x to the 6th. Now, since I just made that up on the spot, I didn't know what it was going to be. Sometimes it's worth your while to combine all the terms. Sometimes it really isn't. So sometimes that can really simplify it quite a bit. Now, when we get to the trig limits, trig derivatives, you'll see that it often pays to rearrange the terms or introduce definitions that will streamline the whole thing. It's often possible to make trigonometric expressions simpler if we know which definitions to plug in or which identities. Okay, so you see what I mean when we get to that point. But here, maybe it depends. All right, now I'm going to tell you right up front, the product rule was kind of messy. The quotient rule, sadly enough, is even messier. There's nothing else for us to do but go ahead and slug it out. Let me just show you what this is all about. So if we assume that f of x is the ratio of two functions, and by the way, I didn't mention this before, but it's understood that when we try to apply a rule like this, we're assuming that both g of x and h of x are themselves differentiable. In other words, their limits of their derivatives exist. Otherwise, none of this is going to work. Okay, so just remember, we're making that assumption when we use these rules that these functions are in fact differentiable. So with that assumption in mind, we can do the same thing here, but here we need that extra assumption that h of x is not 0. Okay, obviously we can't have that. So with this ratio in mind, the rule looks pretty scary. Let's see what it is. Oh my God, look at that mess. Yeah, it's kind of a mess. Maybe it's not that bad, but I mean, certainly it's messier than the product rule. And again, in an in-person class, something like this, you basically would be asked to memorize it. It's not easy, but you can do it. All right. So what we're going to do is, of course, have an example. So let me copy this definition to the next slide. Here we go. Fits right there. So this is our function. These are the two individual functions. So let's start by calculating with the power rule these derivatives. So this first one will be 2 times 3 times x to the 2 minus 1. Now the x, remember, you implicitly have a 1 here. So you got minus 1 x to the 1 minus 1. And this is a constant, so it just goes to 0. So it simplifies nicely to 6x minus 1. So just in general, when you have something like this, If you notice here, we don't have an n. N is 1. N is implicitly equal to 1. So if you have a constant times x, the derivative is just the constant. Now for the h, we're going to apply the power rule twice. And we're going to wind up with 12x squared minus 6x. Okay, so those are the two derivatives that we need. And now it's just a question of plugging in the numbers. Although it's a very messy expression, it's really just now down to substitution and possibly some simplification. All right, so like I said, as scary as this thing looks, it really isn't that bad. Okay, here we go. So I've gone ahead and done that for you. Just keep in mind, so this is h of x, the original h of x, the original g of x. These are the two derivatives that we determined. Ooh, and then this is h. This is just plain h squared. So once again, you can see, you may want to spend some time simplifying it, but it may just not be worth your while. This is fine, unless we need a specific result. All right, so what I'm going to do is make one up right now that you can practice. Because if there's one that really needs practice, this is it. I think that this might be the messiest result that we'll have until we get to the trig functions. And then, even then, it's just a question of being clever with our substitutions. The actual formulas are not any different. All right, let's see what I can come up with here. Something not too terribly messy, just to illustrate what this technique is all about. Let's say that we have this. Okay, so if that's the case, g of x is the numerator. H of x is the denominator. So what you're going to do, oh, and let me just go copy the formula. So what I want you to do is calculate the two derivatives and then plug them in. You don't have to bother simplifying it, just plug them in and let's see what you get. Okay, so I'll give you a minute and let's see what you can do. And so don't forget, with g of prime of x and h prime of x, you're basically just applying the power rule to each term. All right, let's start with g prime of x. So remember, this is 4x. Remember how that works. You can write out the formal rule, but just remember, whenever you have a constant times x, the derivative is simply equal to that constant. So that one turned out very nicely. H prime of x, so again, you have 2 times x. So this is, wow, look how easy that was. Because you have a constant times x and a constant, so that reduces to 2. So when you're done, f prime of x, if you plug in these numbers, you'll get 2x minus 7 times, oh, here it is. I almost couldn't find it. 6x plus 4 minus g of x times 2. And all of that is divided by h of x squared. And that's it. Okay. And again, if there's some good reason for it, you can multiply this out and maybe try to simplify it a little bit, but we can just leave it right here. So anyway, so we've gotten through, actually we got through quite a few of these rules. Just go back and look at the list again. What is missing? I've saved this one for last. Actually, like I was saying before, the chain rule has been saved for the very end of the section, of the chapter rather, because it requires a more complicated technique to solve for it. So these two are kind of complicated. So because of that, because it's Thursday night and it's almost 9 o'clock, I don't think it's a smart move to try to start these right now. This is a very complex topic, so we don't want to rush through it. So here's what I think we should do. We'll stop right here. And next Monday, when we get back together, we'll start with these two. And then we'll move on to the some other fairly complicated ideas involving derivatives, including, for example, the trig derivatives. And then also we'll be looking at how derivatives apply to inverses. And so in the meantime, though, what you should do is make sure you finish the first problem set by later tonight. And then by this time next week, you should have the second one ready. And so next week, we'll pick it up here, and then we'll carry on with what we've been doing. So I think we're in good shape as far as our timing goes. And, you know, down the road a little ways, we'll start thinking about possibly having an exam of some kind, but not just yet. It's a little soon for that. So in the meantime, I guess what I'd like you to do is, like I said, make sure those assignments are done. I'll read through the slides, make sure you understand everything. And then we'll just carry on next Monday night. All right. So if you don't have any last minute questions, I guess I'll wish you a good night then.
Thank you.
Okay. You're welcome.
Thank you, Professor.
Hey,
Thanks,
you're
Professor.
welcome.
Have a good night.
All right. Good night.